Namaste. Good morning, guys. All right, I wanted to do another quick video on power with some examples on the chalkboard, and hopefully this will help you. Now remember, power is the rate at which you use energy. All right, when we say something like an engine is powerful in a car, that means that the engine or the motor can use energy fast. It could change the vehicle's energy very fast. A weak or less powerful motor won't change the vehicle's energy as fast. All right, just want so you get the concept though. All right, so you have, here's one vehicle, here's vehicle number two, here's vehicle number one. If if number one has a more powerful vehicle or more powerful motor, well, actually, let me put it this way: both vehicles, if they start off the line, both will make it from 0 to 60 miles per hour. The one, if their mass is the same, the one with a more powerful engine is going to make it to 60 miles an hour faster. So they'll both make it to the same amount, to the same speed. It says that if you have a more powerful engine, you're going to do that faster. It'll change the vehicle's kinetic energy, in this case, faster than a less powerful motor. And that's kind of what the concept is, all right? I also said something in the previous video that hopefully you already watched. I said that like a gallon of gas can generate an infinite amount of power. All right, and I want to clear that up. I want to make sure you guys actually understand that concept. So let's say that we have a tank of gas, a small tank of gas, or whatever, and the gas totally, if you were to release its chemical potential energy, just to use easy numbers, would give you 100 joules of energy. Let's say you could get 100 joules of energy out of a quantity of gasoline. Okay. How much power do you get from it? Well, that depends on how fast you release the energy, on how fast you burn the gasoline. So because power is change in energy over time, which is also, remember, this is also work, okay? Your energy that can be released would be 100 joules total. If you release it in 1 second, you get 100 watts of power, which is not a lot, but we're just using easy numbers. For the same amount, let's say I burn that gasoline faster, okay? So let's say I still take my 100 joules, all right, that I get out of that quantity of gasoline, and I burn it not in 1 second, let's say I burn it in 1/10 of a second. So my time in this case is 0.1 seconds. So I burned it 10 times, I used it up 10 times faster. How much power did that 100 joules generate in this case? Well, 100 divided by 10 would be 1,000, or 1/10 would be 1,000. So I would have generated 1,000 watts of power, okay, for the same amount of gasoline, just by using it up faster. Okay, and actually, I was telling you about the trade-off. That is the trade-off with at least gasoline motors or engines. That's why they're so powerful. They tend to use a lot of gas in a short amount of time. And yeah, you can screech your tires with it and stuff like that. But the trade-off is that you're using more fuel and you're using it faster. And since they don't give away fuel, all right, it tends to be a bit more expensive. All right, so, but that's what the concept is with the time factor. Just like with energy, there are several equations that go with energy depending on what the situation is. Since power is how fast you use energy, you have several different equations for power. So power, which is work over time, all right, or how much you're changing energy over time, all right, has several variations. If you are lifting something up, then you'd be changing the potential energy over time. And so that'd be like mgh over time. So if you're doing a problem and something is being lifted up, you're probably going to use this version of it. If you're doing a problem where kinetic energy is changing, then, like for example, something is getting faster over time, or is slowing down over time, so energy is being taken away. Either way, you're probably going to use this version, mv squared. Okay, and that's over t, and that's if you're starting from 0. If you're not starting from 0, then it would be okay. So if you're starting, if you're starting at 0, this term goes away. If you're not starting at 0, if the car is already moving, at 30 miles an hour, and then speeds up to 50 miles an hour, all right, that wouldn't go away, and you would keep that. Okay. Sometimes you might use both. So, for example, if a car or an object is going up a hill, all right, you would use both. So the power equation could take the form of delta U plus delta K over T. So it could be mgh plus 1/2 mv squared all over T. Okay, so it could be that also. And there's another version of this too, because remember, power is work over time. It's how fast you're doing work, which is how fast you're changing energy, because work is a change in energy. Okay, work has another variation, so work could be force times distance. So if you have a problem, and you have to look at the wording of the problems. If you have a problem that has forces in it, displacements, you might wind up using this. Now, watch this, because something interesting happens. So power, let's say, takes this form of the equation. So work divided by time, okay? If I rearrange it, d over t, distance divided by time, that's just the velocity. So if you take a look at it, I could rearrange it to look like this, d over t. Okay, and mathematically, this is exactly the same as this. You'd get the same result either way. That's one of those properties, commutative, associative, one of the things that the math teachers talk about. All right, which is one of the reasons why we don't invite math teachers to parties or anything like that. But anyway, you could do that. Now, d over t is just velocity, so power could take the form of this equation, F times V. Okay, where this is an average force and this is a constant velocity. Where would that be used? Well, that might be used in a problem where I have an object like, here's a really crappy car, and let's say, all right, so let's say you have a car and you're just on the highway and you're traveling a constant 70 miles an hour on I-95. Because of friction, the car has a constant 70 miles an hour. All right, it's going forward, but the air friction is pushing it back. But the motor needs to keep releasing energy, it keeps burning energy, it keeps generating power, even to keep it at that constant speed. That's where you would use this version of it. So how much horsepower are you using, keeping your particular vehicle going on the highway at 70 miles an hour? Okay, so that would be an example of where you'd use this equation. And again, you have to take a look at it. You have to take a look at the problems carefully. All right, I have some example problems for you that I pre-calculated. So let's say, all right, so let's just jump into one where we have something going up a hill. So let's say I have a car and its mass is 1,000 kilograms. I'm trying to use easy numbers. Okay, so that's my mass of my car. And let's say it's traveling at 10 meters per second, so that's a V naught. And then it makes it up to the top of the hill, and it speeds up, and then at the top of the hill, it's going 20 meters per second. And let's say that it makes it up a vertical height of 300 meters while it does that. And we want to know how much power was generated by the engine in speeding up the car up the hill from this speed to that speed. Okay, so in this case, obviously you're changing potential energy because you're going up, and you're changing kinetic energy because you're getting faster. So you would use the version of the power equation that looks like this: delta U, delta K over T. So that would be mgh, all right, because let's pretend I'm starting on the ground, like that, and plus 1/2 m, in this case it would be v squared minus v naught squared, because I'm not starting from 0. And let's say I do this in a time, because I need a time here. So let's say it takes the car's engine 100 seconds to speed the car up to that speed. All right, so that would be divided by 100 seconds. So plugging stuff in, all right, I kind of did this ahead of time. MGH, if you plug in 1,000, 9.8, and 300, remember it's the vertical height. Don't use that, all right, when you're dealing with potential energy, it's the height above a 0 point. Don't use that length right there, use the vertical height. Okay, so this winds up being, when you plug that in, just to give you numbers, okay, this term right here winds up being this, and this term, 1,000, all right, that's 20 squared is 400, 10 squared is 100, 400 minus 100 is 300, times 1,000, 300,000, half of that is 150,000, okay, joules. I'm going to divide that by 100 seconds. And what I wind up getting, let me give myself a little more board space here by doing that, all right. When I do this out, I wind up getting that this winds up being, this calculation, 30,900 watts, or 30.9 kilowatts. And if you change that over to horsepower, it's in your notes already, but 1 horsepower is 746 watts. If you change that over to horsepower, you wind up getting 41.4 horsepower. Okay, and you guys can do that conversion. I know you guys know how to convert. Okay, all right, so that's one example of a power problem. All right, here's another example. Okay, so let's say I have a car. It's a really crappy car, okay, and it has a mass of 1,000, all right, kilograms. And let's say that it is, it's a very small car, so its engine has a power rating of 25 horsepower, okay. So it's maybe a smart car, I don't know, something like that. I'm just trying to use easy numbers for examples, okay. And let's say that it's going to maintain a speed, a velocity of 20 meters every second. Okay, and let's say that I want to know, all right, okay, so if this is the power that my engine can generate and I want to maintain a constant speed of 20 meters per second, okay, how much force is needed to, how much force does the engine have to generate, okay, in order to keep the car at that speed? Well, obviously I have, okay, so I have power, all right, and I have a velocity, and I'm looking for a force. So, and remember, that's how you do physics problems. You write down what you know, you write down what you're looking for, and then you go in and start choosing the appropriate equations that you would need to solve the problem. So in this case, if I have a P, I have a P of V, I'm looking for an F, I'm probably going to use this version of the power equation. Okay? All right, so I'm looking for the F, so this becomes force is equal to power divided by the average the velocity of the car. Okay? Now, if I'm doing this in metric, I just have to just make sure you switch over the horsepower to watts, okay? So to keep it all in the same system of units. So I worked that out. This winds up being 18,650 watts. What? I said I wasn't going to do that again, but yet I did. I know. Gianna Truppi, you just snorted right there. All right, sorry about that. I just cracked myself up. All right, I'm such a witty man. All right, anyway, so here we go. And let's see. So the force generated by the engine is going to be 18,650 watts. Kilowatts, again, is a unit that's commonly used too. All right, it's 1,000 watts. It would be, kilo means 1,000, so it'd be 18.6, kilowatts, whatever. And then we would divide that by 20 meters per second. Okay, and if you were to do that, you wind up getting that it's about 932 and a half newtons of force, which, because I'm an American, I don't think in terms of newtons, I think in terms of pounds. When you switch that over to pounds, okay, it's about, the engine must generate a constant 212 pounds of force. In this case, if it's generated by an engine, we tend to call that force thrust. We tend to give it that name. Okay, so 211.9 pounds of thrust must be generated by the engine constantly in order to maintain that speed. Okay, all right, so I just want to give you guys some quick examples of power problems and show you how the equations are used. Okay, so there you go. Good luck solving the problems. See me during my office hours. All right, and remember to enjoy your apocalypse and keep a good crowbar on hand. Goal us out.